In this section of the chapter, we'll look at some actual cases, look at a couple, and they're mostly meant to give you some idea of what we're doing. So we're going to look at proportions first. Next section, we'll look at means. So suppose you have an astrologer that prepares horoscopes, and we take each person whom a horoscope was prepared for, and they fill out this test called the California Personality Index. Now, to see if the astrologer is actually accurate, we're going to compare their reading, their horoscope, with 3 of these California personality indices. One of them is for the person, the 2 are for some randomly selected adults. So, the astrologer is tasked with matching the correct CPI survey with the horoscope that was prepared for that person. Since there are 3 of these surveys, the random guessing would say 1 in 3. But the astrologer claims they know enough from the horoscope to be able to do better than that. So that is a proportion of more than 1/3. So for the hypothesis, the null hypothesis, which we'd like to disprove, is that they only have a 1 in 3 chance. The proportion is the astrologer will get it right 1 out of 3 times. And the alternative hypothesis says they'll do better than that, which is greater than 1/3. So we have a categorical variable. Either the astrologer is correct or not correct. The data is done using randomization. So that's where we randomly had the 2 CPIs mixed with the correct one. And we're assuming the sample size is big enough, so we have to do our test here for proportions. We form our hypothesis, saying null hypothesis P equals some base value, P sub naught. Now, alternative hypothesis has to be one of the 3 following. Either it's better than what we said for P naught, that's greater. It's less than what we said, it's worse, or it's simply not equal. Now, we chose better because we said the astrologer did better than random guessing. If we claim they always do worse, we'd use the less than. If we said it's not either, it's either they're always too low or always too high, it would be the last one. And here's our test statistic, Z. We want to see how many standard deviations away it is. So we take the observed value, which is P hat, minus the proposed value of P naught, and that's the difference between the observed and the proportion, and we divide it by the standard error. You see how many standard deviations away we are. Our p-value we get, doing this is going to summarize the evidence to describe how unusual the observed data would be if the null hypothesis were true. And then we report that and interpret what that means. So in our case, we look at n times p naught, that's 1/16 times a third, and we get a number bigger than 15. We look at n times 1 minus p naught, we also get a number bigger than 15. So we can assume for the sampling distribution that it will be approximately normal. Here's our null hypothesis, alternative hypothesis. Find our standard error, which is 0.0434 or 0.0438. We divide that into the difference between the observed, which is 0.345 minus 1/3, and that 0.345 is how well the astrologer actually did. And we're subtracting the P sub naught, which is the random guessing number we would get. So you could approximate that by 0.333, so it would match the degree of accuracy of the 0.345. And we say the Z is equal to 0.026. Now when we look that up in the Z table, we find the probability to be 40% basically. That the number we would get would be that far away. So 40% of the time, they'll be in that area. Now what we'd like it to be is something like 2% of the time. Saying, well, it only happens 2% of the time, so it looks like if it were p sub naught were equal to this value we assumed, 1/3, then our observed value would only happen 2% of the time. That's pretty rare, so we have to reject the null hypothesis. But it turns out that since we get 0.40, 40%, it's not that small. It's not like 2%. So it doesn't really provide strong evidence against that. So we can't conclude they have special predictive powers. And the value that we got, instead of 0.345, meant something like 0.98. And we calculated this, we would have a very small p-value, like maybe 0.04. Something like that. And then we could reject H sub naught, null hypothesis, and we could conclude that they actually did have some pretty good predictive powers. So our significance test analyzes how strong the evidence is against the null hypothesis. We assume the null hypothesis is true, and then we try to show that in fact it's not true. That's called proof by contradiction. So I might assume that a building is so tall, and then someone brings proof that it's not that tall. That's a proof by contradiction. So if we can contradict the null hypothesis, it actually lends support to the alternative hypothesis. A two-sided one just says t is not equal to p sub naught. That's the two-tail probability. So we'd find the probability in a single tail, and then we double it, so they would be identical. So in this time we're going to investigate whether dogs can be trained to distinguish between a patient with a bladder cancer by smelling compounds released in the patient's urine. That's pretty useful, Dog smells it, gives some sort of signal, and you're pretty sure that person's got cancer. That would be a useful test to have. So for each dog, I tested with 9 trials. In each trial, there was a urine sample from a bladder cancer patient placed among the 6 control urine samples, people who did not have bladder cancer, so there was a total of 7 samples in each trial and 9 trials. For 6 dogs, 9 trials for 6 dogs, 54. And in each of the trials there were 7. The dogs made the correct selection 22 times. So success rate, a little over 40%. Sounds pretty good. But how strong is that evidence? Was it better or worse than with random guessing? So let's check our sample size and see if it's approximately normal. Well, it turns out that n times p sub naught is only 7.7, so it's not large enough. But it also turns out that this two-sided test is pretty robust, meaning even when you don't meet this requirement, you can still use the test most of the time. So there were 7 urine samples for the dog to sniff each time. One of those had cancer, or came from somebody with cancer of the bladder. So by pure guessing, the dog could detect it 1 out of 7 times. So that's what we'd like to disprove, that they weren't actually guessing. So that means if we prove that it's something different, the dogs actually have some sense. So the 0.407 was the observed value we got for a proportion. 1/7 was what we would get from random guessing, and we divide it by the standard error again. 1/7 times 6/7 over 54. 54 is your n value. Remember, n is always an integer, so don't put something like 119.6 in there. That just shows you're not clear on what's going on. So z this time is 5.6. So we looked at this time, and we see the tail probability is some number really far to the right of 0 at one end, and really far to the left at the other end. So a very, very, very small value. So you notice we take those two and add them together, so it's 0.000, what do we have? I don't know, something like 8 zeros approximately, and then a 2. Now that's good for proving this. It's very small, so it suggests that the dog selections are better than random guessing. Now this was a convenient sample. We didn't really just go out and grab some dogs off the street to see if they could do it. But that's okay sometimes. If we do a convenient sample of students to see what kind of music they want played, and we ask outside of Rensselaer Hall, it's not a random sample of everybody on campus, but at least it's relevant. There are people on campus that are asking, and maybe those are the same people who would actually go to listen to music. So, depending on what you have, we have to look at the population and the samples and see if they make sense to actually accept this kind of data. Now, one thing is called validation of other studies. So, if you tested a bunch of other dogs like this, and you got similar results, that would validate what you're doing. So here's a summary of it. Significance level, we choose before we start, just like we choose our hypothesis. And we usually choose 0.05. So if the number we get for probability is less than that, then we set, or equal to it, then we reject the null hypothesis. Otherwise, we cannot reject it. Now, when we reject it, we say the results are statistically significant. So there it is summarized for you. And when you actually have the numbers, it tells you more than just that statement, which is kind of a blanket statement. And they give you some example trying to show you how it's similar to the jury acquitting the defendant. If they acquitted, it doesn't say they're innocent, it just says they're not guilty. Now, there are some things like the binomial test for small samples. Now, you can get away with that so long as the piece of not value is in the middle, pretty much. But if it goes away from the middle, you can't use small samples. And then we're going to do a significance test about means. We'll save that for the next video.